The Story of Everything, Chapter 5, The First Millionth of a Second, the Quark-Gluon Epoch, 10 to the negative 11 to 10 to the negative 6 seconds. Ah! I screamed. The universe suddenly shone with the brilliance of 1,000,000,000,000 suns. Sophia had to adjust my eyesight accordingly. I was engulfed in a brilliant white fog with just a tiny bit of a bluish tint, like a bolt of lightning. I couldn't see my hands or even my nose. It was like being encased in an avalanche of snow, only it was more like a liquid sludge so dense I couldn't move at all, and it was hotter than a brick oven. It is 10 to the negative 11 seconds since the Big Bang, Sophia announced. We have entered the Quark-Gluon epoch, which will last until 10 to the negative 6 seconds, the first millionth of a second of creation's history. A millionth of a second is called a microsecond. A microsecond is very short for humans, but it's still 100,000 times longer than all the previous epochs we saw combined. The weak nuclear force has split off from the electromagnetic force, allowing the existence of photons, which is why the universe is now, for the first time in its history, full of light. Right now, the orb of the universe is about the size of the Earth's orbit around the Sun. But by the end of this epoch microsecond, it will be 10 times the size of Neptune's orbit around the Sun. The temperature is 3 quadrillion degrees. This is more than 100 billion times the temperature of the Sun's core. During this microsecond, the temperature will fall to 10 trillion degrees, which is 1,000,000 times hotter than the center of the Sun. The density right now is still incomprehensible, like tens of thousands of neutron stars being crushed into one. But by the end of this microsecond, the universe will be like one gigantic neutron star that is 10 times bigger than the solar system. Sensing both my awe and claustrophobic discomfort, Sophia said, "Let's shrink down to particle size again so that you can move around a bit and see what's going on." We shrank back down, and it was just like the electroweak epoch. Sophia was letting me see particle waves jostle furiously in dozens of different colors, but this time, with the splitting of the electroweak force, there was actual light, or I guess I should say photons, and a few new particles. "What's a neutron star?" I asked. "And did you make up the word quadrillion? And why did the universe just now feel so thick and hot when it's actually thinner and cooler now?" She replied, "It's because I'm gradually giving you something like a normal human body so you can get closer to truly experiencing what the history of the universe was like, but without being killed. A quadrillion is 1,000 trillion, or 10 to the 15. You remember how small the nucleus of an atom is compared to the electron cloud around it, right?" I said, "Like a tiny bead in a football stadium." "Well," she said, "a neutron star is so dense, it's just those beads. No electron clouds forming a football stadium-sized cocoon separating each bundle of beads from each other. But it's even denser than that right now. I'll explain why that density is important to the Quark-Gluon epoch, but first things first. To understand how the universe will end up with stars and planets and trees and butterflies and people, we need to talk about what's going on in this mess. At this point, Mother, it's probably best that I write you Sophia's discourse in my own words. Actually, my words are partly Sophia's words because, 1, I picked up some of her speech habits from her, or maybe she's adapting her speech to me. 2, she seems to speak partly through my imagination, or maybe she draws my imagination up into hers, so we have a similar voice in that sense. 3, she's the wisdom of all peoples through all ages, so I guess she shares all ways of speaking in common with everyone. I'm also not a very good writer yet. It'll be a while before we get to some of the classics of world literature and I start to learn from the best. I mean, we're only a millisecond into history. Also, I'm writing Sophia's Quark-Gluon speech in my own words because she encouraged me to try this as a way to own what I learned in observing the Big Bang. I'm sitting on top of a very high, cold mountain as I write this, by the way, which is a refreshing break from the hot Big Bang. Okay, on with the show. Mother, the Quark-Gluon epoch is the final era of the historical period called the Very Early Universe, which lasted 1 microsecond. A microsecond is very short. If you blink your eyes, that's 350,000 microseconds. If you snap your fingers, that's about 150,000 microseconds. The time it takes to go from one digit to the next in a digital recording, Sophia will explain to you what things like digital recordings are when she teaches you how to read this book, is a little less than 1 microsecond. You'll be pleased to know that the early universe, the period that follows, will last a good long 378,000 years, and it begins with the next epoch, which is the Hadron epoch, which lasted a whole second. So things will get more temporally comprehensible very soon. I say all that to emphasize that the very early universe is a period so brief that it wouldn't even register in human consciousness in real time. But the very early universe also forms a historical unit because it was the time when the one simple point universe expanded and was shattered into the dozens of fields we now have, which host all the energies we think of as particles, although they're really best described as field ripples. So the very early universe was the period of separating out all the most basic ingredients of the universe. And by most basic, I mean it doesn't get any more basic except for potency and act. That is, the prime matter and forms that make up all the fields, with the forms being little more than the fact that one field wiggles in a different way from another. The ingredients are so simple. First, there are the fields themselves. Second, there are the properties and energies of the fields which flow from the field's form. These fields are extended by space and time so that they fill every part of the universe. And that's it. Those are the ingredients of the universe, now and forever. Fields, and the way they wiggle, and their properties. And the very early universe was about separating all those ingredients out from the one simple singularity. This era was like a baker getting out all her ingredients and laying them out on the counter, with electromagnetism and the weak nuclear force being the last two ingredients she got out. This completed the era of division. While the very early universe was all about division, the rest of the 13.8 billion years of cosmic history will be all about composition. That is, building these basic elements up into ever more complex and beautiful creations. These basic ingredients of the universe are described by what's called the standard model of particle physics, the theory that describes fields and their particle ripples and the interactions between these particle ripples. You see, nature is nothing if not constant change and motion, and this motion derives entirely from the natures of these ripples and their interactions with each other. Existences and their relations. That's one way you could describe all things. And that's as true of the heavens as of the earth, of material bodies and of spiritual beings. So here's the complete inventory of the basic ingredients of the material universe as far as we currently know. There are about 30 or so fields. I'll introduce the fields now in terms of their particles, which manifest the character of these fields. There are two main types of fundamental particle, Fermions and bosons. Fermions represent our modern notion of the building blocks of matter. Bosons represent the four fundamental forces. Bosons represent the war between push and pull that is at the heart of the motion and evolution of the universe. They represent the modern scientific notion of energy, especially the photon, which is pure kinetic energy. It should be noted, however, that all particles can be thought of as packets of energy rippling through fields. So there is no clear line between matter and energy. Sophia says we don't need to know all the properties of fermions and bosons just yet. That is to be set aside for a more thorough study of particle physics someday. We just need to focus on those properties that are necessary to tell the story of everything. With that said, I'll just quickly say that fermions are distinguished from bosons by their so-called spin. The former have odd-numbered half-integral spins, such as 1/2 or 3 seconds, while the latter have whole-number spin, like 0, 1, and 2. But for the purposes of the story, fermions are matter particles and bosons are force particles. We think of fermions as matter instead of energy, in part because they're slow when they have mass, and they don't like to occupy the same space. And so they can be built up into solid objects. Whereas most bosons prefer to fly around at light speed and are just fine with sharing the same place. So they are not suitable for building solid objects. Fermions are divided into quarks and leptons. Quarks are the main building blocks of all material bodies. They come in 6 flavors, but they don't actually taste like anything. I tried. These 6 flavors are grouped into 3 pairs or generations, as are all fermions. There are up and down quarks, generation 1, charm and strange quarks, generation 2, and top and bottom quarks, generation 3. The universe is made of the first generation, up and down quarks. The other 4 only appear in extreme conditions, like in the extremely high energies of the Quark-Gluon epoch and the Large Hadron Collider on Earth. Quarks have a property called charge. Charge dictates whether the electromagnetic force will push or pull. Opposite charges attract like magnets. So that's a pull. While like charges repel each other, kind of like magnets turn the other way. So that's a push. These 6 quarks each have their own antiparticles. All fermions, in fact, have antiparticles, and because fermions are considered matter, their antiparticles are called antimatter. Antimatter particles are identical to their normal matter partners, except that they have opposite charge. So far, we have 6 fields and 12 particles. The antiparticles ripple along the same field as their normal particles. So there are only 6 fields for these 6 particles, and there's 6 antiparticles, for a total of 12 particles. The leptons fall within the same 3 generations as the quarks, and they too come in 6 flavors. What makes the leptons different from the quarks is that quarks have fractional charges, while leptons have whole number charges. For example, the up quark has a charge of plus 2/3, and the down quark has a charge of negative 1/3. But the leptons have a charge of 0 or negative 1. Like the quarks, there are 6 lepton fields hosting 12 particles and antiparticles. There are 3 charged leptons, all having a charge of negative 1. The electron, which combines with quarks to make atoms, the basic building blocks of matter, and the muon and tau. Then there are three kinds of leptons with no charge, or charge zero: the electron neutrino, the muon neutrino, and the tau neutrino. As with the quarks, the second and third generation charged leptons, the muon and tau, are rare. So far we have 12 fields, one for each flavor of fermion. These fields host 24 matter and antimatter fermions. Of these 12 fields, 3 are crucial to the story of everything: the up and down quark fields and the electron field. These 3 fields are the basis of atoms, because atoms are made out of quarks and electrons. Now we turn to the bosons, which carry the 4 fundamental forces. First, there are 8 gluons. Gluons are massless particles that carry the strong nuclear force. Gluons interact with quarks, binding them like glue into clusters called hadrons. When it broke away from the electroweak force, the strong nuclear force followed gravity in becoming an attractive force. But whereas gravity acts on all energies, the strong nuclear force is obsessed with quarks and with keeping them in a tight-knit little community and never letting them go. Bosons are their own antiparticles, which is about the same as saying they don't have antiparticles. So there are just 8 gluons. We're now up to 20 fields. Next, we come to the brand new electromagnetic force, which gave us all the photons of this bright new era. The electromagnetic force could be considered 2 fields: the electric field and the magnetic field, but they host one and only one particle, the photon, so they are usually considered one joint field. A photon is a ripple in both fields simultaneously. And, by the way, photons, just like anything else in the universe, didn't come from nowhere. They are decayed products of the exotic particles in the previous epoch we saw. The electromagnetic force interacts with all charged particles. When the 4 forces split, it became both a pull and a push, like I said, depending on whether the charge of the particle it interacts with is like or unlike. Because neutrinos don't technically have a charge, the electromagnetic force ignores them. Aside from providing the universe with light and heat, the electromagnetic force also keeps electrons bound to nuclei, and it helps atoms bind together to form molecules. Third, we have the weak nuclear force. This force is weird. It's not really a push or a pull. It's more like a magical power. It can boss around atomic nuclei and make them do things like decay and eject particles. The weak force interacts with all the fermions, even the neutrinos. It's essential to making stars shine, which is necessary if you're going to have plants, animals, and people. We'll see what they do soon. There are 2 weak nuclear force particles, the W and Z bosons. There are actually 2 W bosons, one with positive charge and one with negative charge, but they ride the same field. So the weak force just gives us 2 more fields for a total of 23. Finally, there's gravity. But we don't know yet whether this is a field, in which case there would be a particle called a graviton, or whether it is simply curved space-time itself. But we do know of one boson that's crucial to gravity, and that's the final known particle in the Standard Model, the Higgs boson. The Higgs boson is crucial because it confers mass. We will talk more about it soon because the Quark-Gluon epoch is when it first made its presence felt. We now have 24 known fields, 12 fermion fields and 12 boson fields. God likes the number 12. But wait, there's more, maybe. We forgot the inflaton field, which probably exists even though we don't know exactly what it is and have never seen an inflaton. We mentioned that there might be a graviton field. There's the dark matter I saw, so that's at least one field, although we don't know what dark matter is and if it's one or more types of particle. There's also dark energy, which might be considered a field of some kind and might even be the inflaton field. And there's the possibility of considering the electromagnetic field as two, not one. Finally, there may be fields we haven't encountered yet. All told, we have between 24 and 30 fields, and even more types of particles, depending on if they have antipartners. Although different quantities of energy will be funneled into these different fields at different times, ever since 10 to the negative 11 seconds, these 30 or so fields have been with us and will always be with us, and all of them are absolutely everywhere, permeating all of space at all times. Furthermore, they are constantly bubbling with virtual particles. Even the fields whose real particles are rare, like the strange quark field. These are the basic ingredients of physical reality. There is nothing more basic except prime matter and form, which, as I said, is what the fields are made of. Scientists often say that the universe is made of 5 things: 68% dark energy, 27% cold dark matter, 4.9% normal matter, 0.1% neutrinos, and 0.008% photons. What they really mean is that the energy of the universe, which is a true constant, is apportioned in those 5 ways. Note that these percentages change over time, and more radically so the earlier we go back in time. For example, remember that all the energy had moved over into the inflaton field during inflation, but then got distributed through all the fields when inflation ended. But these energies inhere in fields. Inhere means to be in something as a dependent constituent. In other words, these energies are modifications of fields. It is the 30 or so fields that are the true constituents of the universe. The energies are just powers that wander through these fields. The way that, for example, heat flows into your body one moment and cold the next. The primary reality is the body, not the energies that modify the body. The true substances that the universe is made of are the fields. It's worth taking a moment to think about this. Everything you see and touch and taste and smell and hear is built from invisible fields all knotted up and vibrating in various ways. Back during the Quark-Gluon epoch, though, nothing at all had been built yet. There were only the 30 fields and nothing else but their energies and properties. Now that we know what the entire inventory of the universe was and is, we can finally talk about what happened during the Quark-Gluon epoch, the final phase of the very early universe. This was a time when the energy content of the universe was spread more or less evenly throughout all the fields. Everything was in equilibrium, and every particle was crammed so tight that they were constantly bumping into each other. Sophia says that the angels still weren't sure why all the strife between forces pushing and pulling, or why we needed so many fields, but aside from the symmetries of the 4 forces being broken, they still saw symmetry in the fact that every particle existed in great abundance. As for particle numbers, there were just as many photons at this time as there were matter and antimatter particles. And the reason is this: you can make just about anything out of light. Smash 2 photons together with enough energy, And you can produce a matter particle and an antimatter particle. This is called pair production. And there was more than enough energy in the first microsecond to create pairs of particles. How can you make matter out of energy? Albert Einstein's famous equation E equals mc squared indicates that energy is equal to mass times the speed of light squared. This means that energy can be converted into mass, which equates to matter in pair production. But it also means the reverse. Mass can be converted into energy. One way of doing this is by smashing matter and antimatter together. When you do this, they typically annihilate into two very energetic photons, that is, gamma rays. Note that this is very different from the virtual pair production we have already talked about that goes on all the time. The virtual pairs borrow energy from the vacuum in order to enjoy a very brief virtual existence before they meet each other and annihilate back to zero energy. There is no burst of energy when they annihilate, they just vanish. Otherwise, the 21st century universe would be as hot as the Big Bang universe. As a result of the real pair production of matter and antimatter from photons, followed by annihilation back into photons, there was a balance of photons and matter and antimatter particles during the Quark-Gluon epoch. So why was it called the Quark-Gluon epoch? It could have been called the particle soup epoch, which might be more appropriate. But it's called the Quark-Gluon epoch in anticipation of the role that these two types of particles are going to play as the building blocks of atoms, and because of the bizarre fact that the energy and density were still so high at this time that the gluons couldn't bind the quarks together into hadrons, and hadrons are the nuclei of atoms. Even if hadrons could have formed during this first millisecond, the gamma ray photons were so ultra beast mode that they'd blow them apart. But that wasn't the real problem. Ironically, the problem was that if quarks are crammed too close together, the strong force loses all its strength. Gluons are more like bungee cords. The farther apart two objects are, the stronger the cord is. But if you move the two objects close together, the cord goes completely limp. The strong nuclear force is the strongest of the four fundamental forces when you pull quarks apart to their normal distance in hadrons. But if quarks are squashed into a tighter space, the force rapidly diminishes. For this reason, quarks and gluons just slid past each other during this epoch, while all the other particles ricocheted or annihilated or changed into one another. Apart from the electroweak force splitting and gluons not being very gluey, there's one more extremely important event that needs to be mentioned before we conclude the very early universe. I mentioned at the beginning of this chapter how I felt encased in this thick, bright goop and that I couldn't move. But in the previous chapter, we were flying around the universe with ease, and yet the universe was even more dense. Sophia was making a point, and not just about me gradually feeling more of what the universe was like. In reality, of course, my real body would be instantly incinerated and crushed by the extreme densities into the size of an atom. But Sophia was letting me feel a crucial new feature of the universe: mass. Mass is what slows particles down and makes them massive. Not massive as in huge, but massive as in weighty. Mass gives things weight. Mass is what gravity likes to work on. Before 10 to the negative 11 seconds, every particle was massless and light as a feather and zipping around at light speed. But at 10 to the negative 11 seconds, the Higgs boson field broke out from the electroweak field. The Higgs field doesn't interact with photons and gluons, which continue zipping around at maximum speed, But for everything else, the Higgs field is like trudging through molasses. And the more mass a particle has, the more it's slowed down by that molasses. And I felt that dense sluggishness. Sophia has me exaggerating a bit to make a point. Single massive particles like electrons still move at practically light speed, as do nearly massless particles like neutrons. But get enough massive particles together in bonds like hadrons, and gravity will slow them to a halt, thanks to the Higgs field. Heaviness makes people not want to get out of bed, but it's essential in order to make anything solid and weighty out of invisible fields. Without mass, the story of the universe would just be the story of the division of the singularity into 30 or so fields, and that would be the end of it. And while that's the end of the very early universe, thankfully mass intervened, which led to the next chapter and the first truly new substance in the universe since the moment of creation. We're about to witness that epic event and the dawn of the early universe, the era of combining ingredients into new things.